So this is not a secret what I look like. I'm just going to be wearing a mask from now on. My name is Joel. Going to run. Let's see. I've been teaching at USF a couple of years, although there was a break and I haven't taught in a year or so. I've actually, most of my career, I've been a computer consultant. I lived here in San Francisco since '77, and that's what I've done. If any of you are interested in a CS major and want to talk to me about that career path, that's okay. Obviously, you're welcome to talk to me about math. Hi. Okay, so I'm gonna. What? Is that a student who left? You don't seem to have a chair.
I'll go get them.
You know where we can steal another one?
Yeah.
Okay, good. Good.
You want them? Yeah, just. Yeah.
Pausing because I don't want to leave our gracious classmate out. Well, in the meantime, I'll put this up. There's a lot of technology here, and I already deal with too much technology, so I use my own website. You can just go there if you want to poke around and look at, stuff. There's nothing private, but you'll get to where you're going faster by going USF, and then for your class, Math109. Okay, everybody's back. One more try. Tepe Antonio.
Here.
Oh, okay. Soo-Young Choi. Okay. Isabella. Isabella. Caitlin Morataya. Okay. Emily Nam. Okay. And Joseph. Joseph Ning.
Oh, yeah.
Okay.
Sure.
So I've been teaching math on and off since around 2000. Taught at the high school level, taught community college, and now I'm here. All right, so you definitely want to jot this part down. I'll get you to the website. There you're going to find, her name is?
Isabella.
Isabella, okay, good. There you'll find my lecture notes. If you missed a class, that could be useful, or you want to go over something. I'm going to try and put links to videos. I'm going to videotape the class. At any given moment, one of us could be required to not come to class, and I want to try and be as helpful as possible. I also will post homework assignments there, but they're not really assignments until I say so in class, although I'll just put the date on. when they become due. And eventually I'll post the homework solutions. I guess I should say something about homework. Homework really isn't, oh, yes.
Sorry, there's no chairs.
This is Math109.
Yeah.
Oh, and you need a chair.
Yeah.
Okay. Tell me your name.
Isabella is, yeah.
Oh, okay. Everybody's here. Oh, not everybody. Joseph isn't here.
Joseph,
You're Joseph. Okay. Let me take a minute. Let's see if. It's not going to be pleasant with everybody here.
What was your name? Danny. I haven't heard anyone else from Berkeley. I haven't known that she had this school. It's always the best friend I had. It's nice. It's on my floor.
So you have.
But you're from Venezuela.
No, you didn't have. Did you have
Okay.
on campus?
Yeah.
I have a semester and a half. My freshman year.
Oh, he's
Yeah.
from San Luis.
I feel like that's worse.
It kind of tough, you know. We all got sent home over spring break. And they really wanted, they were like, get to the last week.
Yeah, I feel like that's worse than never coming.
Yeah.
So to the people who don't have a desk, my apologies. I will get on it. And by Thursday, we should have more table space. Okay, where was I? How many here are first semester freshmen? Okay, so most of you.
That's kind of stupid.
This is the one part of the class I'm never very comfortable talking about. It has to do with honesty and integrity. We all come from different environments. Some places there might have been a different culture. And I taught places where there was a very different culture. Here we really have high expectations on students. We'll start with your homework. I encourage you to work together on homework. Math can be very productive when done socially, but when you turn something in, it has to be your work. All right? That means you can't go to your friend an hour before class and say, "Can I copy your work?" That's just not okay. It's plagiarism. Of course, obviously during the midterms and finals, you're expected to turn in your own work. That's really all I'm going to say about it. I think you all understand. Have any of you taken calculus before? Okay, a good many of you. That will make the class easier. But this is still a hard class. Taking it before you know it's a class. Mathematics in general, people find hard. And even if you're good at it, you have to concentrate. So I'm encouraging you, this, for some of you being your first year at school, you want to focus on your first semester. Semester is usually the hardest, just because of the adjustment. You get used to the level of work they're expecting here, but don't wait till mid-semester to realize you're having trouble. And I want to also cop to something. This is a really an unusual year. Some of you may have had at-home schooling or remote schooling. no schooling, and you may feel you're a little behind in math. I'm aware of that, and I want to say I appreciate that. I'm going to do what I can. If you're having issues, if you need to come to me during office hours, or if those don't work, let me know. We can always set up Zoom conferences. I want to assist you if you have difficulties in your background. If there's something I mentioned in class today, in class, that you don't remember, interrupt me. Hey, I don't remember, what you do with cosine squared minus, whatever. You're also welcome to come to office hours and talk about background stuff, calculus. We talk about anything, actually. I just want you to know I'm aware of this. I think most of the professors here are aware of this. So, while it will be tough, we're on your side here. Okay. I also want to say you're going to find if you're not already in a well-disciplined person, you're going to become one here. College, you're on your own. You have to make your own schedule. You have to decide how you're going to use your time, and there are a lot of distractions. You got all this social environment. I'm sure now and then there's a party where people get together to have fun, and that's important. But if you let it get away from yourself, you're in charge. So you're gonna have to learn how to do that. And I wanted to say that this university is, in my experience, unique in all the services they provide to help you. So if in addition to coming to see me, you need tutoring, right across the way here is the library. They have a tutoring service you can sign up for. If you start to feel overwhelmed by what's going on, they have counseling here. Don't feel shy. Many students, feel really, impressed by this, their first semester, and okay. I also want to say that I'll fix it, but in my syllabus, which you can also find here, the office hours are off. I haven't figured out how to fix them yet. They're going to be between now and the end of this class and 2:40, and I'm flexible too. So if you need me, just you have my email and let me know, and we'll arrange something. Okay. I want to say a few things about classroom behavior, just because it's different from high school. I'm not going to make this case today because we've got this whole situation with these chairs, but on Thursday I'd like you to pick a seat that you want to stay in. Now the reason is because if we have to do some COVID tracing, we're going to want to, I'm going to want to write down where people are, so we can say, oh, if this person who's in quarantine and people around him might also want to get tested and so forth. Obviously, try to come to class on time. If you're late, just come in quietly, sit down. Don't make a big thing about it. If you need to keep your cell phone turned on, at least put it in silent mode so we don't all know when you're getting a call or a text. Do try and turn your homework in a timely manner. I'm a little bit loose on this. I'm not gonna, I want you to do the homework. It's to your benefit. So if you have to turn something in late, don't worry about it. Don't abuse me. And don't hand me all your papers the day before the final. Let's see. If you need to leave, or either permanently or use the facilities, don't raise your hand. Just go quietly. That happens. You're just gone for a little bit. Come back. If you need to make a phone call, step out and make a phone As I mentioned, the class is pretty long, so I'd like to at least put a 5-minute break in the middle for people to get up and stretch, get some water, or use the bathroom. So if I forget, let me know. I may get involved with what I'm doing and I may forget. You're welcome to remind me. Okay, aside from that, there are 2 midterms, terms, and a final. Please check your schedules. Don't come to me the day before the midterm and say, oh, I have this conflict, I have to go, my gym team is going somewhere or something. All right, work it out now. And that's it. Are there any questions right now about the class? Anything people want to talk about before we get going? Okay. All right. I'm gonna have to rearrange here for a second. This is warm. I guess all the windows are open already? Yeah. All right. Okay. So, mentioned is calculus 109. This is the first semester of calculus. We're going to focus mostly on differentiation, and at the end of the class we may have some time. We'll do beginning integration. So differentiation is about finding slopes. Of course, you're all familiar with the graph of a line. And you're familiar with this idea that what we call M, the slope of the line is y over delta x. The line is going to cross the y-axis, y-intercept, often called b, and we have an equation of a line. So we're going to extend this to a more general function. Here the slope is everywhere the same. On this, it's kind of bumpy. And we're going to look at a point. And we're going to find a tangent at that point. And the slope of the tangent is what we're going to define as the slope at that point. And this, of course, is going to vary. Now, I say tangent here, I've jumped a little here. From your geometry, you're, of course, familiar with the idea of a tangent to a circle. Right? That's the tangent touches the circle at one point. There's a radius, and it's always perpendicular. But of course, on a general curve, we're going to have tangents, and we're not really sure what those are yet. How do we find those? So, all right, just a little more background here. You probably, previous class, learned about velocity and acceleration. And you might be familiar with the formula that x equals x naught plus vt plus, who knows what comes next? Is that right? It's close.
Or AX, these are like 1/2.
Yeah. Okay. So these are constant velocity, well, and constant acceleration. Obviously, if you kind of ignore the acceleration, the velocity is going to be changing, right? Velocity is equal to AT. But acceleration we've always dealt with as constant. And we're going to deal with a non-constant acceleration. And I'm going to be jumping ahead a little here. Back in the good old geometry days, we learned how to find the area of an area that has straight lines. We can always break this up into triangles. And we know how to find the area of triangles. We also know how to find the area of certain curved surfaces, like a circle or maybe a half circle. But in calculus, we're going to learn how to find the area of some arbitrary curve that we have some functional definition of. All right, so I realize for some of you this may be kind of review, and hopefully you're comfortable with it. All right, so now we get to what's going to be the focus of our attention for a few days. We're going to talk about this idea of differentiation. And I'm going to be drawing a lot of very kind of vague kind of curves. And now we're interested in the slope at some point on that curve, which will also be the slope tangent to that curve. Now, if we were to take this function here, and we were to create a new function, which describes the value of the slope at each of these points. Let's see, kind of looks kind of flat, and then it kind of has a peak, and it goes down, has another peak here, and flat, and it wanders around. Okay, not sure if you can see that yet, but we call this the derivative of the function f of x. This is some notation we use. You're going to use apostrophe next to the f. There's some other notation we're going to use in this class. This is, sometimes this is ascribed to Newton, Sir Isaac Newton. one of the say discoverers of calculus. He's given credit for inventing it. There were other people involved, but he didn't actually write it this way. He wrote it this way. All right, but you know, today you're going to see an apostrophe. The other way we're going to see this is like this: d dx f of x. This is attributed to a Gottfried Wilhelm Leibniz. While this is really convenient while we're doing differentiation, Leibniz notation is going to be much more useful when we do integration. I believe Leibniz was French, and Newton, of course, was British. And in the 1800s, it's suggested that Britain was left way behind for many years because of, you know, they wouldn't use this apparently better notation. It's more useful. Now, if I were to describe this in terms of some function, you know, y equals, let's say, some polynomial, we can also describe that as y dx. Now, I want to caution you, this looks like a fraction, right? The d here is going to imply something very small, and it seems like we're looking at, you know, the ratio of two very small things. That's not what this is. You want to, it's okay to think about it that way, but you want to be cautious about it. When you do integration, we even pervert this a little further and we separate them, making it seem like these are finite variables. They're not. This is just notation. So you want to keep that in mind. All right, so let's actually, we're going to do some very, before we're qualified, we're going to do some very simple differentiation here. We're going to start with a very simple function. F of x equals c, some constant c. And we're going to draw a graph of that function. Graph of that function. And we want to know what the derivative of that function looks like. Anybody want to take a guess at what that's going to look like? Yes.
0.
Okay, 0. Drawing a graph. Want to be one more explicit.
This is like a constant, then wouldn't the slope be 0? Because there's no.
This is also a function. What does the graph of the function look like?
I'm not sure.
Okay, that's fine. You're close. Do you want to say what it?
Y equals 0.
Well, okay, yeah, that. It's going to be just going to be the x-axis, right? 0 everywhere, right? So anywhere along here, I want to measure the slope. It's always 0. So this is we're going to start really easy here. All right. So now let's take a step up. And we're going to go back to that graph. This is f of x equals mx plus b, where b is this constant. And there's my delta y, delta x. so now I want to know what f prime of x is. I'm gonna
Is it?
jump around here, yes.
It's M.
It's m, okay, what's m?
It's.
I mean, you're right.
Yes, the graph is
I
like.
want- The graph is,
It would just be whatever the slope is. That it would be a horizontal.
M.
Yeah.
Yeah, it's just a straight line. Okay. It's like, we could have done this in algebra, couldn't we? All right. There's also something interesting here. You notice there's no B down here. Like somehow B has disappeared. If I move this line up and down, the slope doesn't change. B can be anything you want, but it's gone from the derivative. That's a little foreshadowing here. See, if I have some function, f of x plus some constant, and I want to find the derivative of it, well, I get the derivative, but the c becomes 0. And what that suggests is that when you're finding the derivative of the sum of two things, two functions, it's just the derivative of each added together. We're going to get to this. We're way ahead of ourselves. Okay. For all of you in the back who are asleep because you know all this and you think, why is he going so slow? Let's do something. Let's do something that actually you're going to have to work at. Now, I know this is going to sound like I'm jumping way ahead, but I'm not really. The function I want to find the derivative of is f of x equals square root of 1 minus x squared. Now, if you've taken a calculus class before, you may have some idea how to do this. Erase that from your mind for the moment. No calculus. You still want to find the derivative. Well, let's write this as a graph. And let's do the obvious thing here. Roots are always problematic, so let's square both sides. And let's bring the x squared over. Okay, what's that? Everybody here should know what that is. It's a graph. Yes.
Oh, a circle.
It's a circle. I lost my hearing aid here. Yeah, it's a circle. Oh, okay. Well, is it a whole circle? Not really. I mean, this is a whole circle. What about this? We haven't said plus or minus here, so it's always going to be positive. So it's actually the upper half of the circle. Now, if I were to pick a point on that circle, x, y, and I said, what do you know about the tangent to that circle? Circle. We know something about the tangents to a circle. Anybody remember? This is geometry. I guess some of you might have taken it sophomore year, freshman year in high school. It's a long time ago. This is there's something very indicative here of this class. stuff that you learned years ago may just pop up into this class at any time. It's the way math works. I'm gonna give you a hint. I'm gonna draw a radius. What do you know about the radius? Yes?
It's perpendicular to the tangent.
Thank you. It is perpendicular to the radius. Even though I didn't draw it very well. It's a right angle. Okay. Well, that's what I want. I want to know what is the slope of that tangent. And I know it's perpendicular to the radius. Well, let's start slow. If I have a point xy on this circle, what is its slope? Yes?
Y over X.
The slope at xy is y over x. Okay. Everybody see why? It's just here's our delta x, here's our delta y. So wherever we are in the circle, this tells me what the slope is. Okay. This should not be a tough question, but it usually is. How do we find the slope of something perpendicular to something that I know the slope of? Yes?
Do you find the opposite reciprocal of the slope?
Opposite reciprocal. Opposite in this case meaning negative, right? And reciprocal. Well, that tells me that derivative of this function is negative x over y. Now, I'm not happy with that result because I don't really want it in terms of y. I just want it in terms of x. What do I have to do? Oh, well, this is y, right? So it's just negative x over the square root of this x. So without really learning anything special about calculus, we now have a derivative. Let's see if it makes any sense, right? I mean, x equals 0, what do I get? Yeah, it's 0. There it is. I have a tangent whose slope is 0. It's parallel to the x. What happens when I get close to 1 and negative 1 here? What happens to this function? Well, it becomes undefined if you plug it in. But if I'm close to 1, what happens to it? Well, again, that's another way of saying, it's undefined. It gets close to infinity, right? It doesn't get there, right? We never really get there. Well, what happens to this slope as we get close to here? It becomes horizontal, right? And that's an undefined, it's very large. In one direction, it's going to be positive. Over here, a negative 1. Sure, negative is positive. 1 minus almost 1, negative 1. It's going to be very small number, so it's going to get very large. And over here, same thing, only the sign will be different. It's going to be very large, negative slope. Okay. We're going to start talking about something called a limit. And if I get to say something about, we'll say, the history of teaching calculus. Of course, it's very common to talk about limits at the beginning of calculus. But for many decades, the idea was, let's really give people a rigorous view of limits. Let's show them how real mathematicians do limits. And this was very discouraging. We're gonna actually take a look at what that means. I want you to know that, let me just ask, has anyone here heard of a delta epsilon proof? Yeah, okay, that's good. I'm really glad. We got one kind of like this and one kind of like this. Yeah. It's delta, that's the lowercase delta, and lowercase epsilon Greek letters. Yeah. So I'm going to let you guys see what this is about. Don't panic. There will be no delta epsilon proofs on the exam. Anybody here thinking of being a math major? Okay. Because math major, you take a class called analysis, and delta epsilon proofs start coming out of your head. But, okay. So, I just want to clarify, we're going to learn limits, we're going to kind of get a feeling for what they're like, learn why we want to use them, and then we're gonna kind of cheat, in a sense. We're not gonna have to learn rigorous, brain-exploding version. Okay, so let me first give you a little motivation here. Talked about having some function and wanting to know where the tangent of that function is. Well, we can almost do that. We could pick a point, and then we could pick another point nearby, and we could draw a straight line. We know how to do that from algebra, right? You have x1, x2, x1, y1, x2, y2, we know how to figure out the slope of that, right? Hope we do. Anyone remember the formula for that slope? I'm going to assume we have a lot of shy students here. You should know that delta y can be y2 minus y1, and delta x can be x2 minus x1, called m, and that's the slope of this line. Well, we can move that point a little closer, and we'll get a different slope. Let's call this one, I don't know, we'll call it m1, we'll find an m2, and we can get closer, m3, we can get almost there. We can get almost all the way there. The problem is, when we get to where x, y1 minus y1 over x1 minus x1, we're using the same point, then we end up with 0 over 0, which is undefined. Everything just works perfectly fine. You get closer and closer and closer, and then boom. Right, it's undefined. So what we want is we want to create an idea or learn about an idea of some value of m that we get close to. As our line gets close to being a tangent, we want our m to get close to the slope of that tangent. All right. We have a name for that. It's a limit. And we would write it this way. We would say limit as x approaches any constant number. We're going to be using c a lot. Of some function equals some value. This is what our slope here is getting close to this L, this limit. There's another way to write this. You can say as f gets close to L, f gets close to L as x is close to c. Notice we don't say anything about what happens when it gets there. Just that it's getting close to our limit as our x approaches that value where things might pull up. They might. Okay. Now, there's an important feature of this limit idea, which is when you actually get x actually gets to c, it doesn't matter what you find there. The limit is totally uninterested in what's actually at x, or at c. It's just as it gets close. And when I say close, we have to be able to get as close as we want, right? In other words, x equals c plus 1, or say plus or minus x equals c plus or minus 0.00001. You just sit here all day adding zeros. And once you've added as many zeros as you possibly can, you can still add another, right? That's what getting, in this case, what getting close means, to as close as we want. All right. But again, when we get there, we don't care. We don't care what happens. All right. So what we're going to do, I'm going to look at an example here. I want to find out what the limit as x approaches 1 f of x, where f of x equals x cubed minus x over x minus 1. Now, I don't want to be coy about this. What this really is, for our purposes, is x is x minus 1. Sorry, did I write it down wrong? Yeah, I meant x cubed, x squared. This is really x squared over x minus 1 over x minus 1. Now you can see that this is undefined at 1. Again, 0 over 0. But if you look at it this way, you can see there's kind of these two components. We've got x, and we got this fraction x minus 1 over x minus 1. Normally you'd be tempted to cancel this, but that's going to be a problem at 1. It's going to be 0 over 0, undefined. But remember, we're not concerned about what happens at 1. We're just concerned about what happens close to 1. So what is this actually going to look like? Well, f of x equals x squared times 1 most of the time is just your garden variety parabola. And at 1, it's going to be very, because it's undefined there, but it's going to be very close to 1. So along all these points here, we know what it is. It's just FF. It's just f of x equals x squared. Where x not equal to 1. And where it's equal to 1, it's undefined. So here we find that the limit is equal to 1. Function is not, but the limit is. We can get as close as we want to this point, and the closer we get, the closer we get along the x-axis, the closer we're going to get here to 1. So this is a nice, simple example of a limit. I'm not going to compete with the sounding of the bells here. Okay, now I want to consider a very different kind of situation. I'm going to have a function f of x, which is equal to 1 when x is greater than, pick some point c, and negative 1 when x is less than c. So let's see what the graph of that looks like. Another point c here, and greater than c is 1, less than c less than 1. Now I'm not even going to tell you what its value is at c, because it doesn't matter. We're interested in the limit as x approaches c. Well, clearly, as I approach it from this direction, I can get as close as I want to c, and it's still 1. But as I come from this direction, it's always negative 1. So this function does not have a limit at c. All right? Does not exist. We're gonna probably write, this is brand new. It's already dead. It's crazy. So what do we do here? We're gonna often write this as DNE, does not exist. Well, for a minute, we're gonna be interested in limits that do not exist. This is just one way a limit may not exist. You kind of have a limit from one direction or the other direction, but they're not the same. I guess I'm gonna take a little digression for a second. There is such a thing as a left-handed limit and a right-handed limit. If you read through the book, I guess I should have mentioned that. Everybody knows the book for this class is Stewart, edition 9, calculus. Okay. You're going to see a whole section on left-handed limits and right-handed limits. But yes, we can define them, and we may have need to use them, but when we get to them, I'm probably going to do some hand waving. It's not real vital for this class and what we're doing. It's just to add confusion. But But a limit has to be the same whether you're coming from the left or the right. Okay. It's not the only way a limit may not exist. Let's take a look at the function f of x equals 1 over x minus c, and we're going to want to look at the limit as x approaches c. It'll help if we have a graph. Take a look at what this looks like. So we have some value c. C gets very large, the denominator gets very large. So 1 over it is very small. And as we get close to C, it kind of flies up. Think of the line, x equals C. There's a name we give to these kinds of lines. Does anyone remember?
Hypotenuse.
You did say hypotenuse. No, but you're thinking in the right, your brain is in the right realm of obscure sounding words from math. No, it's you know, you get older, those things get really mixed up. It's like salad up there, so you just blurt out things that make no sense. And don't feel embarrassed. It happens to all of us. Yes. Yes.
Asymptote?
Asymptote. Is that what you were going to say? Okay. I love trying to spell. I'm a terrible speller, but I got it right. Asymptote. Okay. It's a line where you just get closer and closer and closer, kind of like a limit, right? How close are we to this? Like a limit. Okay, what happens when we go negative is the same thing, only now it's down here. So as we're getting close to C here, something awful happens. On one side, it goes off as large as can be. The other side, it goes south, as negative as can be. The limit does not exist. Now, as awful as that sounds, there's something even worse. It's just the ugliest thing you could imagine. Well, maybe you haven't imagined it. So we're going to look for the limit as x approaches. Actually, I could put any number here you want. I'll just put 5. Be a little different. Our function is 1 if x is rational, minus 1 if x is irrational. So it's like 2/3, that's rational, so that's 1, and if it's pi square root of 2, it's irrational. And you know how to draw that. There's 1, minus 1. This is how they always draw it in books. You can't really draw it. I mean, you could close in and it would look the same. It's just like fuzz and fuzz with holes and fuzz with holes. Well, here's 5. And as I get close to 5, what happens? We're just jumping around, right? Just jump around. No matter how close we get, we keep jumping around. This is the name. Let's see if it'll come to me. There's a name I can't remember, but it's kind of like insane. This is like an insane function, right? And limit does not exist. does seem a little odd, focusing on what isn't the limit for a little bit.
How much time have I got now?
About 30 minutes?
30 minutes? Oh, okay, that's fine. All right, so now we're going to talk about delta epsilon proofs, not because I want to entertain you, I want you to stretch your mind. I do not want to engage your fear centers. Put your fear centers aside. This is a little trip into advanced mathematics, way beyond where you normally go if you're not a math major. But you can understand this. It's not really that hard to understand, just hard to mess with. And we're not going to mess with it. Okay. So, just saying a limit is a number you get closer to when you get, the function gets closer to when x gets closer to your value. That's not very rigorous. So we need a rigorous mathematical definition of the limit. So the limit, as x approaches c, f of x is L if, I write IFF, if and only if. Has anyone come across if and only if before? A little, okay. Well, when you're doing a proof in math, you have some premise, like A, you say, and you have something you want to prove, B, and you say B if A. So you might, A might be a triangle has base 5 and height 6, and the conclusion would be area is 5 times 6 over 2, right? If A, then B. Now, you wouldn't say the area is 30, so 15. You wouldn't say if you have an area of a triangle 15 that the base is 5 or the height is 6. You don't know that. Base and height could be anything. But sometimes in math, it goes both ways. So we say if and only if. If and only means B if A and A if B. Alright. That's A if and only if B. So this limit thing is going to go both ways. We have a limit and the following is going to be true. And if the following is true, we're going to have a limit. Okay. Told you we were going to use these Greek letters for each epsilon greater than 0. Now, what we're saying is epsilon is a positive number. If you want to think of it as a number small, we can make it really small. We're only really interested in it when it gets small. Now, once we pick, like, oh, it's 0.1, we're interested in all the epsilons smaller than that 1.1, all the way down to, but not including 0. If each epsilon, there exists a delta such that if, now I'm going to explain what this is all about in a second, x minus c, absolute value less than delta, then f of x picture is worth 1,000 words. We have some function. We have some C. The function might be defined at C. We don't care, because we don't care what it's defined at C. It might be like just along this line here, or it might be off somewhere else, or it might be undefined. But we're interested in getting close to L. How close we want to be epsilon close to L. That's what this is. In other words, some place not at C, right? We're somewhere around here. Sorry. We're somewhere close to L. The function, this being, the value of the function. We want to be within epsilon of it. And we take the epsilon value because we don't really care. That's a negative. We're just trying to find the absolute distance to it. What we're saying is if we pick an epsilon, if we can always pick a delta, and by forcing C close to that delta, that's what this statement says. There's the absolute value of x minus C between 0 and delta. We can do that. We can always, given an epsilon, no matter how small, we can find a delta to squeeze it into that epsilon. That's what a limit is. That's not like the touchy-feely, if you get close, you get close. This is the mathematical definition. Now, this is rather unwieldy. And it's kind of confusing because it's, when you think about it, you're going to have to think about things backwards. If I ask you for a limit, to prove a limit, and I'm not going to, I'm just going to show you. What I have to do is find the delta that causes this. In other words, I have to come up with this delta and show that this, then this. This proves this. Or if this is true, this must be true. And although I hear most of you, the number whose limit is 0 will not be math majors, maybe you'll change your mind. Maybe it'll get you enthusiastic. We spend a good portion of a class called analysis learning how to do this. It actually gets fun at some point. So, I didn't really want to erase that. If there's a limit, then this is true. Okay, so we're going to do a very simple limit proof, just so you get a taste of it, just so you can see what it would be like, what we'd be doing every day for homework many times in an analysis class. Let's show that the limit of 2x minus 1 as x approaches 2 is 3. Now, I accept the knee-jerk reaction to say, wait a minute, 2 times 2 is 4 minus 1 is 3. What else could it be? Well, in this case, you're absolutely right. That's why we're doing this problem, because it's simple. Under other circumstances, it's not so simple. Okay, so what we need to do is we need to find the delta greater than 0 such that 0 less than or equal to x minus 2 less than delta implies f of x minus 3 less than epsilon. Now, what makes these things so hard is that you want to prove this, but you can't kind of start with this. You can't magically figure out what the delta has to be. So you work backwards. So let's plug in here. F of x is 2x minus 1 minus 3 is less than epsilon. That's what we want to show. Well, let's rewrite this. So that's going to be 2x minus 4 is less than epsilon, or we can take out the 2. X minus 2 is less than epsilon. Or coming down here, x minus 2 is less than epsilon over 2. Oh. Well, we want to find a delta that makes this true. So we can just set delta equal to epsilon over 2. Now we can work backwards, right? We could say, let epsilon, delta equal epsilon over 2. Whatever epsilon you pick, I'm allowed to choose my delta after you find out that. I pick epsilon over 2, and this tells me that x minus 2 is less than epsilon over 2. So I can work backwards. 2 x minus 2 less than epsilon, 4x minus 4 is less than epsilon. 2x minus 1 minus 3 is less than epsilon. Ah, there we go. I've shown that f of x minus L, that's 3, is less than epsilon. That's what I needed to do. Okay. Anybody needs, you know, like when you get run over by, your arm gets run over by a car and you need to scream out in pain, this is an appropriate time. But keep in mind, you'll never have to listen to another epsilon delta proof like this for me. You may see me hint at one when we go ahead and show some nice features for solving limits. But, okay. Now, I want to just point out something really peculiar about this whole process. Nowhere in here did something tell me what the limit should be. I had to guess that myself. Here I said, no, it's probably 4x. It's probably, yeah, probably 3. Delta epsilon proofs do not tell you what the limit is. So you have to kind of figure that out some other way. And as it turns out, that's what we're mostly going to be interested in doing. And we're gonna look into that. Yes. Tell me again what time it is. And we're good till 11:40. Oh, okay. All right. Well, I'm going to quickly go over 2 little nits that are going to come up. Any questions about this? It's okay, I won't feel bad if you don't. Has anyone seen this before? No? Yes?
I'm a little confused about 4x minus 4.
Well, 2. Wait a minute. May have done something wrong here. wait. 2x minus 1 minus 3, that's 2x minus 4. Is that where you're confused?
No,
It's
the 4
lower.
is minus 4 at the bottom there.
Oh, on the bottom. Okay, let's see, did I make a mistake? There's 2x. Ah! All right. That's worth a candy bar if you find me in front of a candy machine anytime in the next semester. So, yeah, everything else is okay? Yeah, okay. There's a phenomenon some teachers like to say, there's this magic shield in front of the blackboard, and the closer you get to it, the stupider you become. So, I will make mistakes, and I appreciate you pointing them out, thank you. Okay, now I was asking, did anyone ever see any of this before? And someone said no. Okay, that's because you're in a class in 2021. If you were in a class in 1977, they would teach you how to do this and ask you to go home and do a whole bunch of these, all sorts of weird functions, and you kind of work hard, and half of you would drop out of calculus, and then 2 weeks later it'd be like smooth sailing because you'd never have to look at this again. Okay. Before I go forward, like I say, I have kind of two little nits that mostly have to do with terminology you may run into. Is anyone feeling overloaded at this point? You can just kind of wink at me if you don't want to raise your hand. Anyone feeling overloaded? No? Okay, because you've had calculus before. Okay, all right. So, even though I'm not going to be very concerned about it, there is this concept called a one-sided limit. And if I were to write limit as x approaches, and then this is the confusing part, c, put a little plus here, f of x equals L. What I mean by the plus is, I'm finding the limit from, the positive down this way, from big, from this direction. I just find that hard to get in my head. So if I have some function, and it just kind of ends here at c, that's okay. This is sometimes called a right-handed limit. It's not on the right, it's from the right. There's another version of this. I don't think you'll run into it, but in case you do, don't be shocked. I'll put a little arrow. It's going, I guess it would be going down from the right. We'll just, Stuart just uses plus. We'll try and just use plus. At the same time, there of course is a limit f of x as x approaches c minus from the negative direction. And this is called a left-handed limit. Occasionally, like we looked at a function kind of like that, where like a circle, where you can't have a limit at this point because this can't come from this point. It's undefined. Function. It's not in the function's domain. Same thing from this side. And it's a little nit we have to sometimes clean up. but it's not real important to what you're gonna need calculus for, which is why I don't wanna really talk about it that much. And then there's one more, again, it's kind of a nit. You should be aware of the terminology. It's called a limit at infinity. So if we have a function like this, f of x equals 1 over x minus c absolute value, similar to something we saw earlier, then we're going to have an asymptote at c. We're going to find our function kind of goes like this, and as we come at this limit, in both directions, it just gets larger and larger than any number we can imagine. But from both sides. And we have a name for this, well, we call it a limit at infinity. That's a term. Infinity is not a number. There's no number. I mean, not until you get about 3 years later in math that they even try and make infinity a number. Infinity is just a concept. It just means just bigger than anything, any number. We will write this with an equal sign. Stuart will. Not equal to infinity. Infinity is not a number. That's how we'll write it. And I want to encourage you to try and think this as notation. It has meaning, but not the usual meaning. It doesn't mean with some value. Okay. Any questions, either about what we did today, about something about the class, about what you did on your summer vacation, Then we are finished for today. I'll hang out here a little bit. Sometimes students have particular things they want to bring up to me. And if there's ever anything you want to talk about private, I'd like to talk to you in your office sometime. Okay. Thank you.
Thank you.